Okay, this is William again. Brand new day, and today I'm hoping to finish out the rest of the mechanical series of Swerve Drive. Um, Stop off last time. So, um, if I remember correctly, um, last video went over some of the past Swerve Drives of other teams, as well as looking at some of the Swerve Drives that I ran personally on my old team. And what worked well, what didn't work so well, and all this. Um, but today we're gonna sort of focus on one different design family and a module that I've designed just for exercise for myself, but also for a greater breakdown of a sort of module. So I feel like in the past videos we've gone very cursory, looking at just overarching higher concept design decisions. But for this video, we're gonna get even more into the details of it, and to an extent that even I don't think it's necessary. I don't think that the application specific details of each and every Swerve module are really necessary to go over, just because you know every application you're using it for is different, and who can say that one type of Swerve module is what works best for your robot when every robot is different. And to that extent, I'm going to try to design a module or show you a module I designed and show how I've integrated it into a chassis, just because I feel like um, that's the sort of thinking you have to have. Beyond just designing a Swerve module, you have to put serious thought into how you're going to mount it to a chassis and create a rigid frame. So this, I'm going to go back to my 2018 robot, my 2017 robot to show contrasting um, sort of chassis design style. So this is kind of a cross in between, but let's look at this. So this is the 2017 Swerve Drive module I ran my junior year, and as you said before, this is sort of the Revolution Pro 2 module style. Super thin, so not very wide at all, but very long. So it's 3.5 inches by almost 11 inches. Makes for something that gives you a lot of front and back clearance, but it completely takes up the lengths of your robot. And we're going to see in some of the modules from like West Coast Products, aka 1323, and SDS, aka 2910s modules. And instead of choosing a bias one way or the other, they have modules that symmetrically mount, so that on the left, there is no, it's side agnostic. So it creates a robot system or a chassis where there is no defined front, left, right, or back due to the geometry of your modules. So of course you can establish a front, left, right, back, whatever, but it's not constrained by your Swerve Drive modules. Whereas for these modules, where there's clearly a thinner, there's a rectangular system, sort of a square mounting system, you're sort of saying from the get-go that, hey, some parts of this robot are going to be closed off, and some parts aren't going to be closed off. Meaning that you can intake probably from one of two sides, or intake from both sides, but you can't intake from you can't intake perpendicular to a mechanism or whatever. Whereas with other module designs, there's flexibility in there. And furthermore, we're very familiar with like mounting things to box tubing. But what my team did was like we didn't actually have these rectangular modules. What we did is we machined it all out of one gigantic plate. And see here, they're all like made of different components, but in reality, when we machined this, it was just one gigantic plate. I don't know if it's on hand, but assume that. So it was a 25.25 by 20. So we basically took like a 26 by 24 plate of 1/4 inch aluminum and machined this monster plate. And the name we called it the mega top plate because it was a lot. It was a huge piece to which we mounted all our Swerve Drive modules. So this is one form of a chassis assembly, and it works well because in this form you don't have to add an extra inch of clearance on the perimeter of your robot to account for the 1 inch box tubing. You just have the entire just have your storage drive module plates be an integral part of your chassis, which is what the SDS and West Coast Products modules do by like connecting the tubes. But here, this chassis design just threw away the idea of using any tubing built on top of this base. As you can see here, there's no box tubing. The bumpers mount almost directly to chassis, and everyone's really happy. Do you note that we had to do some really funky things? We had to create a wheel well in order for the wheel to not hit the bumper wood, and then we had to raise the bumpers up, down accordingly. It was a funky robot to get in order to pass the rules. And 2018, we kind of followed the same idea, but instead of having one mega plate, we had 2 plates, and you see sort of merging back with the traditional box tubing or extrusion manufacturing philosophy. We had 2 really big side plates that are connected together by pieces of extrusion and one bigger underlying belly pan that constituted the robot. So that's more what you would see in a common robot. But if you watch a tank drive, or you know what tank drives look like, or what even modern Swerve drives look like, they don't utilize full plate assemblies like these. They more commonly look something like this chassis. So something with if I remove the bumpers, it looks like this, where it's 4 pieces of rectangular tubing and Swerve drives mounted at all these points. So serving as gussets, like really big gussets, to connect the chassis at the top, and a big belly pan at the bottom to connect everything. So this is more in line with what we'd see. You would see like you'd put your robot mechanisms all on the top here, and there are benefits to both construction techniques. I would say the primary benefit of this is that you don't need to create. There's no need for a really big sheet metal. You could do away with this belly pan. You don't need this big belly pan. You could just have corner gussets at every point. But if you ignore that, then all you need to do is have a mill that can create 2 length pieces of box tubing and these smaller plates which can be made probably on a mill or a not super big router. So that's what I'd say is a more common thing. It's also I think the benefits also that there's more common mounting points. Here you with plate construction, with only plate construction, you get to push your modules as far out to the front, to the sides as possible. It means that mounting is more of a problem. You can't mount things to the sides as easily. But again, it's all a matter of how you want to do things. Just generally with box tubing, it's easier to mount things. It serves as a template to put everything together and allows you to form square chassis. But this works just as well. It's just a bigger commitment to whatever designs you have, and it's saying, okay, whatever we build, we have to make it adaptable to this plate construction. Whereas with box tubing, you have more freedom in that regard. So what I showed you before, this chassis is derived from the West Coast Products, SDS modules, where it's a symmetrical design. So instead of being fat, instead of being thin and long, you have a pretty like stubby module, and it doesn't. I think from top to bottom, it's maybe 10 inches. So that's So from this midpoint, it's 7.6 inches, and it's a 4-inch wheel, so you add in 2 more inches. So there's 9.6 inches from top to bottom. And compared to this module, it's a little bit taller than that. So this is a 4-inch wheel. So this is 8.6 inches versus 9.6 inches. So with the West Coast Products module, it's a full inch taller than than what I consider to be like the most compact storage drive I ever built, but in a different style. I would call that squarely like the Rev Pro 2 style. And this is something that like I would say West Coast Products and SDS really pioneered in recent years. It is bevel beside wheel, thin radial bearing, so thin thrust bearing setup. To note, I don't think this is actually a X contact bearing. I think it's just a normal large bearing. I can't actually tell. And yeah, they lower the clearance a lot by removing that additional gear transfer here, and at that cost, the cost of that was making a much wider wheelbase here. So they sweep out a much bigger circle here. They don't mount the motors on top anymore. They mount them on they don't mount the motors on the bottom anymore. They mount them on top. Like that's a very like clear visual thing. And so the um the clearance they cut here is immediately gained back by putting the motors back. But the ultimate gain is the symmetrical mount. So now instead of having a thin and long module, they have what is like a square section. So the tubing gets on rectangular tubing, it gets joined here, and this top plate of the storage drive acts as a gusset. The same for the storage drive specialties module. You have 4 holes, spaced out an inch apart, and they mount nice and cleanly to whatever module you use. On the top, they look very, very similar. I very few changes, which is just how they mount. And that's sort of what I want to take away from these modules. Um, so when I design a module like every year really, just to brush up on CAD, to um, see what I need to work on. And here in my latest iteration, I said, okay, I want it to mount symmetrically. Like I don't want to have to create mirror assemblies of each other. In order to make this chassis here, you needed to have mirror images of each other in order for them to work. And because it was all on one plate, you didn't have to make mirror assemblies to make it all out of one plate, but you have to design mirror assemblies. So I said, okay, I don't want to have to create a mirror assembly. And next thing I thought, okay, I don't want to use stacked needle bearings, and I don't want to use a copper bushing. I want to use one of those slim X contact bearings that SDS has used. I don't really know what West Coast Products uses, but either way, I want my bearing to be seated within the main plate of the storage drive, and I don't want to worry about it beyond that. And then this is where I diverged from their thinking, and I said, okay, I know what I want to take away from this, but I like having low ground clearance, so I want my motors to mount back at the bottom. And in order for my motors to mount back down the bottom, I can't have this really I need to add height here and lower the width of this sweeping motion. So that means that I wanted to basically narrow this. Because in order to put the motors back down the bottom, I had to create like space here. Otherwise, I'd have to make this whole module bigger. And that was a big thing. I knew what worked, but I didn't want to, and I really wanted to stay within those bounds because this is 5.5 inches from flat to flat. It's 5.5 inches from here to here. And I said, okay, whatever I do, I don't want to take up more space than that. And I managed to end up staying pretty close to that. It means that I could not do a bevel beside the side wheel setup. I mean, there's some benefits to this. There are some benefits to not doing bevel besides wheel. Mostly that I don't need to rely on a fairly niche product or something you buy from China and mill yourself. You can just use bevel gears and very 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 common gears that you can buy from Dex or HandyMark. And the benefit of that is that you can also avoid using this really big gear, or in SDS's case, a really big custom billet pulley. You can use either 3D printed stuff or the COTS pulleys. In my case, I tried to use a COTS pulley, but in an effort to reduce profile, I ended up using 3D printed pulley that was still much smaller than this. So we can sort of walk through that. I think the Falcon, the West Coast products and the Swerve these modules, kind of all have this convergence to the same design philosophy, and I've kind of mashed it up together my modules. Back to chassis, and we're gonna see here the Swerve drive module that designed. So it's kind of I think it looks kind of neat because it's a combination, it's a mashup between two families of design. So here we see the Rev Pro 2 style. And instead of using the Vex bevel gears, we use the HandyMark bevel gears because they have a lower height. So they take up less height, and then we can kind of compress the module more. Besides that, there's very little changing from the Rev Pro 2 iteration to this. It's simply bevel gear. On that shaft, we have then spur gear reduction to a 3.25 inch wheel. So this 3.25 inch wheel would really only work in a game of very flat ground. So if there was a 1 inch bump, really I wouldn't want to use this setup because my motors are so close to the ground. But there are flat games, and there are many games where this direction works fine. And I'm not saying this module is a solution for every single game. Just proposed to be one design. So the leg assembly is pretty standard, and I think where it gets kind of cool is it uses a K-Dom bearing, so X contact bearing. Instead of a 3.5 inch bore, it's a 2.5 inch bore with a 3 inch outer diameter, so it's a full inch smaller in diameter, and it takes up much less space. It's retained the same way as the West Coast products modules, so there are bolts on the top, bottom to sandwich the bearing in place, and that's the main thing. So that's like the main cool thing here, is that it's like a melding designs, and it's all in the sake of keeping robustness. That's a key priority, and beyond that, making things more lightweight and more compact. Let's go up now, show you the weight. Everything modeled out, materials assigned correctly. I'm coming in at 4.7 pounds, which is drastic improvement from past modules that utilize the Rev Pro 2 design family. Here the module motors are pretty similar, and we'll get to that later. We can go through like the exact free speeds and everything at a later point. I'm not gonna go super in depth into free speeds and drivetrain speed calculations in any of these videos, just because I've gone through them once already. Characterizing a Swerve drive is significantly different from characterizing a tank drive. And there's not as much of a science that's been put into it, and I don't have enough to refer. But we will go into it. For now, I'm just gonna try to break it down component by component. So as always, the meat of the module is always in the leg. I call it like the drive column. So we went over we just went over the biggest thing, which was integrating the Kadon bearing into the system. But then there's now the rotation aspect of it. So beyond driving power to the bottom wheel, there's a matter of how do we actually turn the module. And so we can consider the Kadon bearing and this rotation pulley kind of separate from this leg, and it has to connect to the leg in a few key spots. What we can see here is that this rotation pulley, which is driven by it being about 550 on a versaplanetary gearbox, on a 1-to-1 pulley reduction, that's driving the whole rotation of the module. And that's connected all together by this hub. So you make this hub not visible. The pulley is a 3D printed part over here. It's a 44 tooth HDD 5mm pulley, and it's printed out so that it fits perfectly the shape of that COTS hub. And there's a bolt that goes through that hub, through the pulley, through the bearing shaft, which is just a thin quarter inch round piece of round stock, through a nylon shim over here to space out to avoid the module hitting the bottom bolts, and through into the final plate. And this is what I was happiest about in the in this design, because it leverages a COTS part, this anti-mark bearing bore hub, to connect everything. So this is one of the most crucial parts in every single swerve drive design. Something that's going to take a lot of load and needs to be like carefully machined or designed or bought. And in my case, this is a part that's going to be 10 or 11 bucks on AndyMark, and fits our needs perfectly. It's pretty thick wall. So generally you want to have close to a 1/4 inch thickness in wall to get everything to fit through. For everything to fit through in the middle, but also to, oh, can't change settings. Okay. But it's thick wall, so it can take big loads on any side. It's not going to bend or, it's not going to bend, deform anyway. And it allows every single part in this module to be co-located. So every single part in this system has a 1 3/8 inch bore, and the AndyMark bearing hub goes through all of that. So it keeps everything very well centered, which I think is very important. So beyond just having everything just bolted through, the nuts here are, I think, not really supposed to be there. If you note, this is threaded for 832. So what's happening there is that the whole pulley system is just bolted all the way through. But then it's additionally co-located by this bearing bore hub. So that is what I'm happiest about. Like, because technically you don't even need this. The whole thing would technically run, but because everything's made out of plastic, you need to have, well, because the top pulley, the steering pulley, is made out of plastic, you really want to have a strong aluminum piece in the middle to really absorb most of the load, because otherwise your plastic pulley is going to deform or crack or bend or whatever. So most of the material inside has just been not printed or removed and been designed to make room for a entire bearing bore to fit. This gives space for the shaft to fit through and for you to mount a bearing at the bottom. So instead of putting a bearing at the top, like into the actual hip, it's going through the bearing bore to again guarantee concentricity. Anything else? I'm really happy about that design because otherwise I'd have to design plates to be CNC machined to adapt to all this. This thing is it's a pretty complicated part to make on a mill if you have to make your own custom solution, and being able to say and being able to just take something off the shelf and kind of repurpose it for a Swerve drive column, I think is pretty neat. This is called the bearing. I call it the bearing shaft, mostly because it's what's actually riding in the bearing. So if I make this shim not visible, you see that what's kind of inside and resting in the column of that Kadon bearing is this bearing shaft. It's pretty stupid. It's just a round plate, 4 holes going through. They're not. I don't think they're not actually tapped. I think I tapped it for no good reason. They're just through holes. And there's a 1 3/8 inch inner diameter for the handy mark hub to fit through. That's what's inside the thrust bearing and taking that right to the leg. That shim visible. I mean, at that point, that's kind of it. I'm not going to go into details. We have the leg. There's a bore for the top shaft, 1 1/8 inch bore for the bearing. The bottom, it's a dead axle, so we're not putting anything through. We're just putting in 3/8 inch shaft, which is serving as a dead axle for the wheel, and we'll just kind of spins freely on that. The whole thing is connected by a series of bolts and brackets. So it's not one billet piece, and they're not like nicely milled legs. They're leveraging here the small mills or small router capabilities that a lot of teams do have. Where there's nothing here that requires 3D machining. Everything's through. All pockets are through the whole surface. All holes are drilled all the way through. And besides that, you're just making contours on metal. It is required to flip apart and then drill precise holes in those locations. If you have a mill like we do, like 2Train does, this is really easy to do. And I was designing in mind of 2Train. I was thinking, okay, how can we design something that we can really easily make in-house at 2Train? So we have a water jet. We have a new water jet. We have our trusty fryer mills. These parts are really easy to make. Okay. There's not much going into that besides there's a lot of bolts. Are all these necessary? I would say maybe you can get away with removing this top bolt on both sides, and then that's still pretty. There's not much more to go into. Besides to note that there's like very little clearance. This bracket barely clears this gear. This wheel barely clears the bevel gear. This bevel gear, like it's like it's practically kissing the gear here, but it's not. Missing an E-clip here, missing an E-clip here. So a lot of like really tight tolerances that screwdriver is really that going like that bolt is nope, it's the most marginal clearances. Well, bolts aren't the big issue here. We can always cut down bolts a little bit more. So this whole thing is very, very tight. In an effort to make things as low as possible, everything is really, really, really packed. Just to go over things. It mounts symmetrically, but the actual module itself isn't symmetrical. What that means is that you don't have to create mirror plates, but you do have to reassemble. You have to create two modules that are assembled differently from the other modules. So everything is made the same way. There are no like different plates to make, but they come together differently. And from side to side, it is 5.2 inches side to side. So technically it's a smaller profile than the West Coast products or the Swerve specialties modules, but because of the thing sticking out the backs here, does it really count? Like, I don't count it, but um, technically it's a smaller profile than anything else. So that's that. In general, I'm not gonna say it's smaller than those modules, but it fits in a small package, which is really what I wanted to achieve. I wanted it to not take up a lot of space. What I'm truly happy about, and I'm not skipping on anything here, is the height. From bottom to top, it's only 6.8 inches tall. I think that I'm really happy with. So this is bottom of this 3¼ inch wheel to the very top of the plate. So this is a full 3 inches shorter than the West Coast Products module. I wish I could kind of just drop it in place to show you the rest of the modules, because this is really, really, really compact. It's shorter than the other modules I've designed in the past, shorter than modules that I used in high school, and shorter than a lot of the other modules that are available on the market. This also gives you a ton of clearance on the top to mount more mechanisms. It means you can mount your intake. Your intake doesn't have to like be thinner because it's not constrained by side to side heights. Because generally your bumpers are mounted at the 7-inch portion. So your intake is going to be resting over bumpers usually, if it's a full width intake. And if your modules are below that bumper height, then you're in pretty good shape. So this low profile module really allows for a lot of things to play with. So that's what I really, and that's all made possible by the leg being as compact as possible. Because the motor and everything, as long as the motors don't hit the floor, and they're actually pretty close at this point, as long as the motors don't hit the floor, they can kind of go wherever. What drives the height of the module is the height of the leg, or the drive column, or whatever you want to call it. Everything is extraordinarily compact here for a reason. Everything is as close as possible to each other, because without that, it'd be a 1/4 inch, an 1/8 of an inch, whatever, however many fractional inches taller. And every single optimization there is intentional so that I get a lower and lower profile. And that's why, Swerve is so hard to do, because unless you buy it, you have to hold these tolerances. All these parts have to be machined perfectly, within at least under 5 thou, ideally less than that. Because the second you start missing tolerances, the second is when these parts actually like hit each other. If this connecting hip, bringing everything together, isn't something else. Okay, yeah. So everything needs to fit really well together. And let's say if this connecting hip is like machined to be 5 thousandths too short, then this bevel gear starts to hit this gear. It won't turn anymore. It's all over. Or then this gear starts to collide this plate. It's a disaster. So everything has to be held very tightly. This nylon spacer offset to make sure this bevel gear engages this bevel gear has to be machined to what is like 500ths. Otherwise, it's not going to engage, and you're not going to drive the shaft at all. So everything is really, really tight. Let's go for it. So this is the connecting hip. It connects two legs and the brackets that hold everything together. It's, again, I would call it a simple part. There's a bunch of drill ops, and it makes making it really painful because you have to flip it over a bunch of times, you know. But it's not too bad. Like you couldn't even, I don't think you could even drill through all the way on these sides because um, you're probably not gonna get a drill that can reach all the way through. Like you need at least like probably 2.5 inches of drill exposed out, and you just would never want to have that much drill length out like that. You can maybe get away with it for drilling through here, but even then, you probably just want to flip it over and drill again. And for all of these holes, you have to tap them. That's the most painful. A lot of tapping and drilling. So that's that. This is the steering pulley. These are generated with a HDD pulley program that I downloaded. It's just a simple Java program that generates a TXF file that I then extruded from. But there are a lot of generators out there that you can use to get these profiles. From there, like I kind of had a generic pulley stock, and into that I added on all these additions. This is what that like generated profile is. So this is the generated profile, and from there, from this 44 tooth pulley profile, made this, and this is to be 3D printed. This is the bearing shaft as you went before. This is the thing bringing everything together, the anti-mark bearing hub. Again, I just think it's super neat that it's a COTS part, sort of not for its intended use, but also kind of for its intended use. This Swerve drive. Okay. Here, so maybe I should even put a bearing here to further support the hex shaft, but that's not. I don't even think that's even necessary. Okay. So that was a leg, and then we have main plate. There's honestly not much to talk about, like technically, because most of the effort that went into this is trying to position the motors so that you can minimize the space taken up as much as possible. And that's what I did. I just basically spent hours, not hours, but I spent significant time just moving around. But not this sketch, sketches. I don't know what I just did, but apparently when I changed that sketch, I destroyed this profile, destroyed this rib. But playing around with these sketches, so this is where the turn gearbox mounted, and I had to move it around basically until I found a satisfying place for that to go. And this one was a lot more troubling because it was the drive gearbox, so I had two parameterized holes for that main plate to go, and I had to just move them around until I found an optimized place for them to go. At the end, this main plate was cut out. Back to the Swerve module, everything's coming together. The VP, planetary gearbox, mounts over here, and the Falcon or Sim or Neo, whichever you want to mount, mounts over here. Note that you could use one any of those three, Sim, Neo, Falcon, and they would all fit. Nothing would interfere, so that's pretty good too. Driving a pinion to a 32th gear to one final to a pulley reduction down to the. So I think something that I could even do in the future is avoid this extra reduction and instead we mount the Falcon higher up and just run one pulley reduction here and down to leg. The reason why I didn't do that is because with this pinion I could move the Falcon closer to the VP and then thus cut the length this way. So here I'm sort of adding complexity for the sake of compactness. You know, I kind of sacrifice the simplicity of having just one simple plate. I think it's a sacrifice it's worth giving up, but it tacks on a lot of manufacturing and space errors. You have to multiply everything out 4 times in order to make 4 and then there's this top plate which holds everything together. It's what pushes the whole module down, keeps it constrained to the floor, and this is why I call it the middle plate, which is kind of a dumb name, but all it does is it constrains the shafts from the top. It's pretty lightweight. This is the hole for the drive shaft, this is for the turn gearbox, and this is for the initial direction of the shaft. Visualize here. It's not like it's derived from the main plate geometry, but it's like dramatically smaller and more pocketed because you're not supporting a big 3-inch outer diameter bearing, not supporting a motor and all that. All you're doing is constraining the shafts and adding structural rigidity to everything. And something that I'm even unsure of is that this bearing is supported on like it's cantilevered out. There's no final standoff supporting it over here, but I think that's kind of forgivable because we really care about supporting the module here. I don't think there's as much of a worry to ensure that this standoff is very rigidly mounted. Because I think it's already very rigidly mounted, and I don't think there's a need for there to be a fifth standoff holding everything in place. If you think otherwise, let me know. It's not a challenge to put that. I'm not gonna go into the details here. I mean, I will go into them, but not to, like the thinking behind them. I'll just go into like the speeds. The last piece of like mechanical thinking that went into this module is the steer pulley. So in the past, we used an SRX mag encoder, so a third slice here, and to avoid using that, just to get the extra ground clearance, because otherwise we'd be really, really close to the ground, I switched to this Lamprey hollow bore encoder, and this product came out just this year, and it serves the same purpose, but power versus there's a magnet comes with this encoder, and you have to adhere it, glue it, whatever, to the shaft you want to detect rotations on. So you glue it to the shaft, and there's a PCB over here, encoder that reads the rotations of that magnet. And it has to be mounted in a band of distances. So it can't be closer than 0.15 inches, and it can't be farther than 0.5 inches. And right now, I think it's... Oh, so this actually has to be mounted higher up. That's not an issue. Let's say 0.2 inches. Okay, perfect. So that is how the encoder sensing on this works. There's still some significant backlash that, not significant, but if there is backlash on the system, this encoder isn't going to really get it, but it's, I think, a good enough solution for what's happening. The only slippage that we're going to see here is if the belt slips, and if the belt slips, really no encoder is going to be able to get it unless you're on the final shaft. So here, and that is like a possible scenario, and all I'm saying is that I'm hoping that doesn't happen, and that because it's a 1-to-1 ratio, the encoder, this Lamprey encoder, can detect rotation just as good as it could have, just as well as it could have if it were on the final reduction here. If that's the case or not, there's no way to say yet, but I'm hoping, trusting that it does, that the tension is good, that there is no belt skipping here. Okay. So moving on from that, the same thing. So this is another 44 tooth pulley, derived from the same template from before, and it's kind of the same thing. Because it's plastic, you want to really use a metal hub to reinforce the part because you're turning with a lot of torque, and you don't want to be driving a plastic part. Some teams have made it work with really well designed 3D printed parts, or using Markforged filament or Onyx filament, or just nylon filament. And while I'm sure that would work if you really designed it well, I don't think there's a need to do that when you can just put in a little extra work and figure a way to get aluminum hubs that are mounted securely and provide all the load-bearing material stiffness that you need. So here, if I remove the hub, see that on this 3D printed part, I've kind of designed on pattern of a hub, and the hub just interfaces nicely and gets bolted on 3 spots between top of the pulley and the bottom. And the hub sticks out a little bit, and from here to here is, I think, 0.19 inches, and that's the exact height of this magnet, 0.19 inches. So this way, the magnet is flush with the pulley, it glues on nicely, and it's ready to detect for the lamprey encoder. So everything works out nicely. That's mostly it. There's not much to go on besides that. And yeah, that's the module. I guess now we'll go into free speeds and then go into sort of the chassis, but that's mostly it. Yeah, let's go into the chassis. Let's go into the speeds. Okay, so this is the JVN designer. Here, the way to consider how do you think about a storage drive if you were to characterize it, you'd think of it as if it were a 4-motor tank drive. In this case, it's not a differential drive, if you know what that means. It's just a 1 motor per module to drive the wheel. So akin to a tank drive, there are 4 motors in the drivetrain powering the speed, like just the wheel, and you can input that into a custom 1-speed drive. Because we're not going to say it's a tank drive. We're really considering it as there's 1 module at each corner of the robot, and each corner is holding approximately a quarter of the robot's weight. So we're not going to put in there's 4 motors in the gearbox. It's 1 motor per gearbox. And we're going to consider, all we're looking for is this free speed output and everything that comes out of that. So speed loss constant and whatever. Drivetrain efficiency, I'm not going to play with these values because they really mean nothing, and all they do is affect this adjusted speed, and we're not going to worry about this at all. All we're doing is just playing with a nice drivetrain free speed. We have a 3 1/4 inch wheel, and these are the ratios. I think this is an 11 tooth gear, but because it's an undercut invalid gear, you can use a 12 tooth gear, and they'll both fit in this 3/4 inch profile. It drives this 30 tooth gear, which then drives a 30 tooth pulley to a 42 tooth COT Vex pulley. That goes down to the 1-to-1 bevel gear transfer, down to a, I think, 34 to 54 tooth reduction, or 32 to 54. Wait, 34 to 54. So the bevel gear, you can't treat it as just a straight 1-to-1 transfer. There's more significant heat loss and inefficiency at this interaction due to the crown gear interface, where um, they don't transmit power as well as spur gear reductions do. So there's a greater efficiency loss there, but we're not going to worry about that too much. So go back to, let's say we have 11 to 30, 30 to 42, 34 to 54 reduction. And so it gets us for a final drivetrain free speed of close to 15 feet per second free speed. You watched the other video, like this is a little bit fast, but overall, for this year's game, 2020 Infinite Recharge, it's, I think, a reasonable speed for full court sprints. And there's no shifting gearbox. But if this direction were, say, like a trench runner that didn't traverse the rendezvous zone and were only to take shots at the trench zone, or even then, if it were a target zone shooter, it'd be fine because you never want a Swerve drive to be directly pushing. And because of the reasons that I just mentioned, where there is a lot of inefficiency in the bevel gear transfer, and if you're just pushing straight on, yeah, you're gonna get 4 Falcons all turning the same way, but you're not getting as much pushing power due to that heat loss. So really, you never really want to be in a pushing match. Because first of all, if you're in a pushing match with a robot, you already lost as a Swerve drive. Like, that's not what you're building a Swerve drive to do. And you're probably going to lose that pushing battle, and you're wasting time that you really could have just been scoring. What you want to be doing as a Swerve drive to avoid defense isn't to like push it away with brute force. You want to be, navigating around it. Be a ballerina, not like a wrestler. So that's the speed calculation on that. But I'm not going to go into the dynamics of that and characterize its sprint speeds and stuff because I did it once with tank drives, and you can kind of do the same thing here. The key considerations are really that you're not drawing too much current, and it says the pushing current draw is at 180 amps, probably cap that at 150 anyway, and you also never want to be pushing that high anyway, unless you're like just starting up the motors. So it's not totally under spec. I think this speed is fully within the Falcon's capabilities, and you don't want to be pushing to extremes anyway. You want your Swerve drives to be sort of nimble and not like beefy. So this is the mirror Swerve drive module. It's the exact same parts. All I did here was flip the plates around and reassemble it, which wasn't too big of a deal. It just means that if we were to make this in real life, it'd be a little bit harder to do. And chassis itself is pretty simple to make the bumpers not visible again. It's 4 pieces of box tubing, all of half-inch hole patterns, and these modules fit right on. So they serve as gussets on the top, and key thing here is that the wheels clear. Look at the bias. See that these edges never interfere with the walls, so there's clearance at all points. These legs never hit here on the belly pan. This is probably where I'm closest to potentially hitting anything. And see, it's very, very close, but clear. If you're worried about the motors hitting the ground or hitting an obstacle, they're not really, kind of a joke at this point, but I made these motor guards. They're transparent because I don't really think they're necessary, but they're 3D printed motor guards that fit over. And then this is more thing about now chassis integration. If you look at the Swerve module, there are these, there's just like floating spacer and this floating bracket, and those are used to mount to the chassis. So that floating spacer is used to mount down to the belly pan, and this floating bracket is used to mount to the belly pan as well. This is kind of nifty. This is actually using the vent screw on the Falcon. It's a bracket. So there's a hole here that's usually meant to connect your fitting, a pneumatic fitting to, and to plug that to your system so you can blast air into your Falcon to cool it down. A lot of things find it unnecessary, so I'm planning to take out that vent screw and replace it with a bracket so I can then mount it to my belly. I think it's super necessary, and you could just easily not have that because I had the time. I decided to put, um, so that's all in thinking about the chassis itself and not confining yourself to the Swerve module. Because when you're designing your Swerve module, you want it to be robust relative to your chassis. In isolation, if it's a strong Swerve module, that's great. But when you're connecting it to everything else in your robot, you want it to be integral to everything else. You want it so that when you put everything together, it's very solid and not going to break. And that's the reason behind, not just cutting off this bracket here and extending it down to the belly pan, connecting the Falcon to the belly pan itself. So there are multiple points of connection, and there's a more solid connection between every single component in the chassis. Another nice thing about having a lower swept out profile is that you can also have ribs coming out all the way. And this really should be adjusted to meet that rib, but you can sort of close off this what would normally be like a huge rectangular cutout to be multiple ribs holding in the belly pan. This is the belly pan by itself. It's pretty run of the mill. First you go first like a rectangular cutout and the first diagonal lines. I pattern that out, and I kind of cut out the additional stuff. This cut removed all the extra lines, and from there I added in all of this stuff to the previously just like straight up crisscross pattern, and that constitutes the chassis. All in all, it weighs 38 pounds, but if you subtract 10 pounds for the bumpers and everything, it comes out to around 28 pounds. And so that's again heavier than a normal tank drive, but at a pretty healthy weight. You're not crippling yourself by running a Swerve drive. Yeah. So that's mostly all there is to say. If you're curious about anything else, like very cat specific, I'm happy to answer those questions. But this is just sort of a component breakdown of the Swerve drive that I've designed, and it's not meant to like give you direction on anything. It's more just a case study in action, and I did it because I'm more equipped to explain something that I've designed personally than I am to explain something that it's like a product that someone else sells. So I designed this module just for my own benefit and also so that I could better explain it to you, because otherwise I wouldn't be able to explain the design choices of West Coast products or SDS. And also it allowed me to design my own chassis for it, which allowed me to like optimize for certain things that West Coast products modules or whatever don't have as much room. So that's mostly it. I think the key thing is this is a module that 2Train could really easily fabricate compared to some of like the big billet pieces that we saw in parts. I don't think create this wheel in house, and I don't think we can make that pulley in house either. West Coast products, the products are a little bit more feasible for us. Like these legs are not impossible for us; they're actually very doable for us. But I made it a priority. So it's just that we minimize the 3D printed parts to be things that like absolutely needed it, and everything else was sort of just plate construction. Really easy mill operate, mill the parts. So I think this is a Swerve drive that's like especially like tailored for 2Train, but also very custom. Do I think a solution of just buying a module from West Coast products or Swerve drives such as these would be the right move? I think that would totally work, but as an engineering thing, as just a design challenge, I think designing your own Swerve drive is always a fun thing to do. It's always a great educational opportunity. It's how I sort of got really into first by learning about Swerve drives and learning how to design them and math, programming, and the mechanical aspects of it. And for a lot of things that don't have the mechanical abilities to put together a tightly machined thing like this, the SDS or the West Coast products modules are great because it gives you time to focus just on the mechanical aspects of it, on just the programming aspects of it, and not need to worry about machining really complex things. But I think for a team like us, even though we aren't necessarily the most competitive team, I'm not saying that we should build this module to be competitive. I think um, designing a custom storage drive is just great to do it for the learning purposes. It would be great to do this just to learn more about design, learn more about manufacturing, and learn about our programming capabilities. Um, so I'm gonna cap it off there, but I hope this was uh, fun to look at, and all these models we made available. Like just check the summary below in the video. See a link to all these drivetrains. Okay, so with that, I'm gonna sign off. Thank you for watching. If you watched.